In our previous week, we discussed about the discovery of subatomic particles, and we focused on the developments done by important scientists like J.J. Thomson or Ernst Rutherford and Chadwick, and how they came to the evidence for the existence of electrons, then protons, and finally neutrons. In this week, we will continue in this line, but we will see in detail how some of the previous theories of the 18th century, they were proved and improved with the new technological advances like X-ray absorption or X-ray diffraction. And we will also discuss on how these developments could help to understand some molecules like, for example, chlorine gas or the resonance structures. So for this, we will have to use some of the materials we discussed in the previous session, and we will start with the case of radioactivity. From the previous session, we know that this type of radiation was composed of three components. So one of them being the alpha radiation, the other was the beta radiation, and finally the gamma radiation. From the previous session, we know that the alpha particle responsible for alpha radiation was composed of two neutrons and two protons. The beta radiation was the radiation of electrons, so it was an electron. Just in the case of radioactive elements, it is called beta radiation. And the gamma radiation, which is a light like radiation. So it is not a particle, but it's more like a wave of light. So, so first, to talk about radioactivity, we should begin with Marie Curie. As we discussed in the previous session, she was working with uranium and thorium, and she gave the name of the process itself. So she gave this name of radioactivity to this phenomena, to this radiation. The problem with the radiation of uranium and thorium is that the signal or the radiation itself is quite weak, and because of that it is difficult to use or to experiment with this type of radiation. However, she was working also with some uranium ores or some minerals that contain uranium, but she realized that some of these samples it had some more intense than expected radiation, or it was more radioactive than what could be explained by uranium itself, by the uranium content in the mineral. Therefore, the conclusion was that in those minerals there should be an, another component of a different element which is also radioactive but is contained in a much less concentration. It was then that in 1889 she discovers polonium in July, and in December of the same year they discover radium. And this, the last one, radium, it is a very rare element, but it's 300,000 times more radioactive than uranium. And with this, then it was more easy available, the use and the experimentation with radioactivity. Now we will talk also, I mean, like in the case of other scientists, like for example, J.J. Thomson or Andre Sommerfeld, Marie Curie was also the supervisor of other famous scientists, like for example, André Louis de Debierne, who was a PhD student of Marie Curie, and he discovered himself a new element which was also radioactive, which is actinium. So now the list of elements which are radioactive started to expand at the end of the 19th century. And in the 1900s, then Friedrich Ernst Dorn, he discovers radon, which was interesting because it is a gas. So also even gases can be radioactive. And in 1917, protactinium was discovered by Otto Hahn and Lise Meitner. And then a new list of elements with these properties is discovered, and typically these materials which are radioactive, they share something in common, that is that radioactive elements have atomic numbers above 83. So this is something that we know today, even though there are some exceptions, just a couple exceptions. And next, with all this new knowledge on radioactive sources and the knowledge which was built at the end of the 20th century on radioactivity, it was Ernest Rutherford, the person who gave like a next step, and he used what is known like a particle gun. So what he did is that he puts a radioactive source embedded or closed by a lead box, let's say, with a small hole where the particles from the radioactive decay could be like shot, like a gun. And what he put in front of this was a metal sheet or a mica as well, and he recorded the particles which were able to pass through this gold foil or this barrier, and putting a photographic plate behind. And even by counting the strikes of particles against this photographic plate, he could detect how many particles and what angle were the particles deflect. And this is important because if the particles are able to go untouched, so they keep a trajectory which is linear, let's say, so it means that the alpha particles were able to pass through thousands of atoms of gold, in this case, without being deflected. Or it means that the space, how they travel, it was empty. So they traveled through an empty space. But he also noticed that some of the alpha particles, they got deflected at different degrees. So even some of them were able to bounce back. So it really means that in the atoms, there are also some structures that are at least as massive as the alpha particle, which is able to deflect the alpha particle while traveling. So, and this deflection is also a sign of the charge. So, what he concluded is that the atom was mainly a structure of empty space, but it must contain a positively charged nucleus that was able to deflect the massive alpha particle. And this is important because if you remember from previous session, it was thought that the electrons were attached or glued to the positively charged center or nucleus. And now with this Rutherford theory of nuclear atom is getting closer and closer to the atoms we know today, or as we know them today. This also had some important consequences because like this, it could be explained that chemical reactions only interact with this outermost part of the atoms, which are far from the nucleus, and therefore all these chemical reactions which were described in the centuries before Rutherford could be explained only by small changes in the outer electrons that were far from the again were far from the nucleus of the atom. So the chemical reactions only involve this thin, let's say thin layer of electrons at higher energy levels. Now, in the next video, I want to show you a modern version of the Rutherford experiment, proving the deflection of alpha particles through a metal film.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles, They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom is empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing them at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small and the atom, by comparison, is very big. So it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
And now with all these new resources that we discussed, for example, in the previous session, and with this new model developed by Rutherford, then the question would be, what is the difference between one element and the other? And the way to answer this was from the use of X-rays. So you should remember from a previous session when we discussed about the discovery of X-rays, starting with the cathode rays, that Röntgen himself, he discovered this by accident, but immediately it was proven to be useful in fields like medicine when he collected the X-ray of the hand of his wife. But now in 1909, it was Max Theodor Felix von Laue who applied X-ray to crystalline structures, to crystals. And this with the scope of recovering some information about the crystal material itself. So, and what he discovered is that these crystals are able to produce some regular patterns, and this pattern is related to the geometrical features of the crystal. And then this is a technique that we use, it's a daily technique that we use in research for the identification of crystalline structures, or how is the arrangement of atoms in a material. But it's not only about the diffraction of X-rays, but it was also discovered that elements give rise to a particular set of characteristic X-rays, and this is another technique we know like X-ray spectroscopy. This was discovered by Barkla, and it will take an important consequence for the next scientist, who was Henry Moseley. About his life, we know that he died in the First World War in Turkey. But before that, in 1913, he was able to conclude that the wavelength of the characteristic X-rays is inverse with the increase of the atomic weight of the elements emitting them. And the inverse relationship, he was able to explain it by the size of the positive charge on the nucleus of the atom. So by using this development, he was able to demonstrate or to determine the nuclear charge of the elements. And then we got this series of hydrogen, which is +1, helium +2, lithium +3, and so on. And this nuclear charge is what we call like the atomic number. So now, with this new model designed by Rutherford and with his experiments that showed that at the center of the atom there was a positively charged nucleus, and around it you can find some electrons to make the element neutral. So it was the necessity to make a model to organize these electrons. It was Arnold Sommerfeld, a German physicist, who gives this name of electron shells. About Sommerfeld, we can say that he was a very influential professor in Germany who was supervisor for 4 Nobel Prize winners, like for example Heisenberg, Pauli, and so on. And also he was the supervisor for 3 postdoctoral students. So in total, he was directly connected with 7 of his students were Nobel Prize winners, which is a impressive result of his career as well. About electron shells, it was Barkla that we mentioned him in the previous slide, who gave the names of or these letters to each shell. So he assigned the K, L, M, N shells that later it corresponds to the principal quantum numbers that we, as we call them today, with n values 1, 2, 3, 4, and so on. What is important about these shells is that each of them, it has a limit of electrons that it can hold. For example, the K shell can hold only 2 electrons, while the L shell can hold only 8 electrons, and the M shell as many as 18, and so on. So this gave some order to the way how electrons could be placed, and it also showed the energy level for each electron. And this is important because, as you should remember from previous slide, the chemical activity of a compound depends on the outermost shell, because this is the shell that makes collisions between atoms and responsible for the interaction, let's say. And we know, for example, that from the periodic table that alkali metals, they have 1 electron in the outermost shell, while alkaline earth elements, they have 2, and inert gases, they have 8, and so on. So each group that you can identify in the periodic table, they have that each group that shares chemical reactivity or chemical activity, they can be identified by the number of electrons in the outermost shell. And this is interesting, or most interesting, in rare earth elements, because their atomic numbers can vary significantly, for example, from 57 to 71, but all of them share chemical activity, so some chemical activity which is common between them, and this is because of all of them share the property of having 3 electrons in the outermost shell. Another important contribution on the influence of electron shells or these electron configurations is made by Richard Abegg, that he says that during a chemical interaction, what is or the driving force of this chemical interaction is to reach the inert gas configuration. So for example, in the case of sodium chloride, it is desirable for the sodium to give up 2 electrons, and for chlorine to gain the electron in order to achieve the electron configuration of an inert gas. So sorry, sodium gives 1 electron, and chlorine accept that electron, and in that case, you form 2 ions that they interact each other, so they attract electrostatically, and at the same time they reach the inert gas configuration. But this suggestion by Abeggs, it is known like the electrovalence. It is useful to understand some chemical interactions, but not all. Like for example, there was a question on a molecule like chlorine, because if the only principle or the only mechanism to understand this chemical interaction between atoms is through Abeg's suggestion, then chlorine will not the chlorine molecule will not exist, because in that case what you need is that what chlorine needs is to take one electron in order to achieve the inert gas configuration. So there is a difficulty to answer or to explain a molecule like chlorine. So it was Gilbert Newton Lewis and Irving Langmuir who developed the concept of covalence, in which they proposed that that atoms are also able to form, which is called like a shared pool of electrons, in which each of the chlorine atoms is able to give to share one electron in the pool, and these electrons will place in the middle of the two atoms. Therefore, both electrons are able to achieve the inert gas configuration. And this is also able to form a bond that requires some energy to break up. So it also gives some energy that allows the molecule to be stable. Both of them made important contributions, like for example, Lewis. Well, all of us we know about Lewis structures, or the definition of Lewis acids like electron pair acceptors, or Lewis base like an electron pair donor. So with all these contributions, he was nominated 41 times to Nobel Prize, but he didn't get it. On the other hand, Langmuir also made important contributions, mainly in the field of surface science, and he was awarded with the Nobel Prize. The next important step was taken by a French physicist called Louis de Broglie, and his contribution was that he was able to demonstrate the theoretical reasons to consider electrons to possess wave properties. Later it was Newton who also showed that waves can have also like a particle behavior, and for the case of electrons. And then we have this dual concept, like the wave particle duality of electrons or particles. And this is important because it helped to understand some chemical process like resonance and some stabilities shown by compounds like benzene that we discussed also with Kekule's contributions in a previous session. So what is important about these wave properties is that it helps to understand that the electrons can move through the molecule more freely than just to particles that are fixed to a specific location. So if the molecule was considered like flat and symmetrical, then it could be expected that the electrons can move freely through that molecule. And for example, in the case of carbon-carbon bonds for benzene rings, it was demonstrated that if you consider the electrons to have these wave properties, then the carbon-carbon bonds in the ring should be all the same in energy values, I mean. And this is called the resonance hybrid, and this is what is happening in reality. So the resonance acts like an averaging factor for the bonds between atoms that are subject to the effect of these electrons. So resonance can explain, for example, the three-dimensional structure depicted by Van Hoff. If you remember, he made an important contribution when he proposed that carbon can form this tetrahedron structure at the time when everything was considered like planar. And with these wave properties, it can be understood, because if you consider the case of carbon and how he is able to form four electrons, so the valence of carbon is 4. So he has 4 electrons in the outermost shell. But each of these electrons, they are different to each other, so they occupy different energy levels. So you will not expect the bonds of the carbon atoms to be the same. But if you analyze a molecule, a tetrahedron of carbon with, like for example, CH4, then you would expect some differences in the energy of the CH bond, because the energy value for the electrons in the carbon are at different levels. However, this is not the case. And if you check these carbon-hydrogen bonds, they are equivalent to each other, so they are similar to each other. And this is because the wave properties of the electrons allow like an average wave form for the 4 electrons in carbon when doing this type of tetrahedron structures. And the person who made this analysis of resonance, it was Linus Pauling. And finally, we will talk about some radioactive materials, but more precisely about the half-life and isotopes. And at first, we should talk that there was some empirical evidence, mainly by Crookes, that uranium samples increase their radioactivity with time. So it was known that the radioactivity of uranium was weak, as we discussed before, as in the case of uranium and thorium. But what Crookes noticed is that after time, this radioactivity started to increase. In order to explain that, it was quite logical conclusion that after the emission of an alpha particle, then the atom has to change, because it lost 2 protons and 2 neutrons. And remember, if you lose the protons, then you change the atomic number, and therefore you have to move at least two, no, at least no, you have to move 2 positions in the periodic table to the left, because you lose the 2 protons. And in this case, after the emission of the alpha particle, what you end up is with an atom of another element. And this is also an evidence of, or an explanation for the reason why minerals that contains uranium also contain other rare radioactive elements like radium or polonium. So what is possible to conclude is that the radioactive decay or the breakdown of a radioactive atom brings another uh, element, which is, if you have the emission of an alpha particle, then you will change 2 positions to the left in the periodic table, because you lose 2 protons. And what is also interesting, and it was measured by Rutherford, is that the rate of radioactive breakdown is characteristic for each element. So for example, the half-life of radium is 1,600 years, while that of uranium is 4.5 billion years, and thorium is 14 billion years. So by using this knowledge, it was possible to determine the age of Earth. Like if you consider this radioactive series and you have a sample of a uranium mineral, or a mineral containing uranium, but besides uranium, you are able to trace the amount of lead, then you will be able to determine what is the age of Earth, because you know what is the rate of decay of the uranium sample to lead. And in this method, it was possible to conclude that our planet has an estimated age of 4 billion years. But soon they discovered that after the decay of a radioactive element, a new atom, a new element was formed. Like, for example, from uranium-92, it is possible to produce thorium-90 by the emission of one alpha particle. However, this thorium, which was produced from the decay of uranium, is it has a half-life of only 24 days. And if you remember in the previous slide, we said that thorium has a half-life of 14 billion years. So what they found with this is that elements, or better, as Soddy says, that more than one kind of atom could fit the same atomic number. So it means that in the periodic table, we have the atoms arranged by the number of protons. But if you can satisfy that requirement of number of protons, but having different number of neutrons. And because of this difference of protons and neutrons and electrons, then you will end up with an element which can be defined by the same position in the periodic table, but being more or less or with a rate of radioactive decay faster or slower. And this was discovered also for other elements in 1912 by J.J. Thomson, who, in a similar fashion like he discovered electron, in this case he subjected beams of positively charged neon ions to the action of a magnetic field. And what he discovered is that he was able to form two distinguishable spots in his detector. And one of the spots was 10 times more intense than the other, meaning that the concentration of one of these flux of neon atoms was 10 times higher than the other one. But also it means that the other one exists as well. So these isotopes, they could be found in most of the elements of the periodic table, but not all of them. And even more, it was found that isotopes could exist in even hydrogen. And then it was Harold Clayton Urey who discovers deuterium, and he published this figure to the right, where you can see a very intense broad signal from hydrogen 1, which is in the center of the image, and a very weak gray line to the left, which is the signal corresponding to the heavier hydrogen 2, to the deuterium. So this is the material that I wanted to show you for this week, and see you in the next one. Thank you.